Hi, and welcome back to EEG Tutor. I'm your personal EEG tutor, Dr. J. Case McKay. Today we're going to cover adult sleep EEG. Hopefully this topic won't put you to sleep, but it's very important to understand what you're looking at during most clinic recordings and a lot of hospital recordings as well. So let's get into it. All right, here's an overview of what we'll cover during today's lecture on normal asleep EEG in adults. I'll essentially take you through the lightest stages of sleep all the way into the deepest stage of sleep, which is rapid eye movement sleep. We'll cover the features of each of these stages of sleep, and admittedly there is a bit of memorization of how these sleep patterns should look. The principle for today is that a complete EEG involves sleep. You tend to see certain features of an EEG better during sleep than wakefulness. There's less artifact. You may actually be more likely to see epileptiform abnormalities, that kind of thing. So essentially you want to capture sleep if you can in a routine EEG to have the best idea of what's going on. So drowsiness is really the initial transition from wakefulness to sleep. You look for something called slow roving, or some call rolling eye movements. I'll show you what these look like. There's also attenuation of myogenic artifact. The patient, is becoming more relaxed, so they have less myogenic artifact, less tension. Then you see some shifting of the alpha rhythm more anteriorly with slowing. You may also see some burst of theta during this stage, and really there's kind of an artificial distinction in a lot of EEGers between drowsiness and N1 sleep. In a lot of sleep grading scales, they're kind of just the spectrum of the same stage of N1 sleep. You start to get into basically seeing drowsiness here with slow roving eye movements. If you pay attention here, you will see that there are some changes, these slow waveforms here. What I'm getting at here is that you see that there are slow roving eye movements. If you remember back to kind of the direction of where they're looking in the eye and how that would create the positive deflection, you would see that this patient's at this point is looking to the right, and then the eyes go back and they're looking to the left, and so the eyes are just sort of slowly going back and forth to the left and the right. And this is what you get when you have your eyes closed and you're drowsy. Here's another example of this, and remember to orient yourself to the montage as well. So you often see this best in the frontal temporal kind of regions, and so if you remember back to that diagram of the eye movements, you'll remember why. But again, you start to see this patient's eyes just slowly moving back and forth, creating these slow waveforms, and this is very typical of drowsiness. You may also start to see the background slowing, getting more theta frequencies, kind of moving from an alpha to a theta predominant background, and you start to see a shift of the amplitude kind of more towards these anterior electrodes than when you're awake. And these are all features of drowsiness. As you transition into N1 sleep, you start to get a little bit more features that are interesting. Here you're starting to see some burst of theta, and to me these are still kind of in the drowsy spectrum. And then we'll start to cover post or positive occipital sharp transients. And what happens is you get polarity that's positive in the occipital leads. This is going to lead to a waveform that looks quite like a lambda wave that we previously covered. And these are typically seen bilaterally, and they're seen in those really with intact vision. You need an intact visual system typically to generate these. And they can occur in trains as well, of about 5 hertz, but they're usually more isolated. All these here are post, all these waveforms in the occipital region. They're kind of lambda really in shape, and you see them, they're symmetric. This is a good example of what they look like. Epileptiform discharge, which we'll cover later, but just remember this is positive. And this is a feature you'll see on most EEGs you're looking at. Here's a bit more of a subtle example, but you still see them. These are post as well. This may be all you get depending on how well the patient's brain is generating the post. And again, you see it here in the occipital on the left, occipital on the right, and then occipital in the central occipital electrode, which this montage has. Vertex waves are another feature of stage N1 sleep. These occur as trains sometimes. Just like any other stage of N1 sleep feature, you can still see that during deeper stages of non-REM sleep, in particular into stage N2 sleep. You may still see these features overlap with the features of N2 sleep. So vertex waves look like this. They phase reverse centrally, and they have a broad parasagittal field. So this is a vertex wave here. You know, they look a little scary to the untrained eye. They may be kind of epileptiform because they can be sharply contoured at times. So when you see something over the central head region that with a strong phase reversal, more or less at CZ, and you give it a little bit for some technical, wiggle room. It may not exactly be on CZ, but pretty much on CZ centered there. You want to always think about it being a vertex wave first and rule that out before you start trying to call an abnormality. It's pretty rare to have an abnormality in this region, so you want to think vertex wave first. Here's another example. You see a phase reversal here that's really best seen in the parasagittal and central area. So CZ, phase reverse, has a negative phase reversal here, and then you see that same thing at C3, C4. This is what a vertex wave will look like during sleep. Here's, you get some trains of them, and they start to look a little bit scarier. And this example is just to remind yourself when you see something like this to think vertex wave first before you start trying to call something wild. Sometimes you can get sleep variants that look like a little bit more angry like this, especially in a younger patient with more defined features in non-REM sleep. All right, so stage N2 sleep is a deeper stage of non-REM sleep, and it's characterized by sleep spindles and K complexes, which are some of the most well-known features of non-REM sleep. You may have seen that before, even in medical school. You may continue to see the positive occipital sharp transients or posterior occipital sharp transients in vertex waves. Sleep spindles are something that you're going to really think kind of high end of alpha or low end of beta in terms of frequency. Frontocentral parasagittal predominant waveforms, they're usually about 1 second duration and become less prominent with age. You can see longer sleep spindles, particularly with children, younger people, and they're thought to be generated by synchronous cortical and thalamic firing, secondary to a drop in cholinergic activation, which is occurring during non-REM sleep. Here's what they look like. This is a characteristic kind of textbook sleep spindle, kind of around a 12 to 14 hertz kind of waveform here, and they last about a second, and they're maximal in the frontocentral regions. You see them best in the parasagittal electrodes, though the field does blend into the temporal electrodes, particularly in the frontal areas. And then again, you still see some vertex waves mixed in here too. Like I said, you can continue to see those features of stage N1 sleep during N2 sleep. Here are again some sleep spindles, and you recognize them by the frequency and distribution, as well as the other accompanying features of sleep you'll typically see. And these are a little bit harder to identify than the ones we saw the first go around. These are even harder to see. These are sleep spindles as well. Orient yourself a little bit to the montage here. It's a little funkier. You got the parasagittal chains up top, central here. And so you see them best here, and this kind of a subtle sleep spindle here in a patient that's asleep. And so this is on the slower end of that 11 to 16 hertz. K complexes are also basically pathognomonic of stage N2 sleep. No one really knows where this name came from. Some say it was called a knock complex because you can kind of stimulate them by having a noise. This is thought to potentially preserve sleep, the K complex, and they're likely also generated by the thalamus. And you see them look basically like this, at least kind of two phases to it. And I tend to think about it like kind of someone's head rocking back and forward. It doesn't really have any true relevance, but it always helps me remember it especially when I was learning. And these big waveforms are kind of delta style waveforms. You also want to not mistake them for some type of delta waveform encroaching into the background because they're actually a normal feature of non-REM sleep. And you see them here again, a bit more prominent. And this example also kind of a subtle mixed sleep spindle in here. And here's another example of a bit more subtle K complexes. And you have at least two phases, one phase, two phase. And these waveforms, are going to vary a bit depending on the patient's age and all that. But you'll typically see something during stage N2 sleep when it comes to a K complex. You may only see it right as about the patient's alerting. If there's a noise or something like that, you might see it then as well. As you progress into non-REM sleep, you eventually enter slow wave sleep, which was called stage N3 sleep, and sometimes stage N3 and N4, but basically it's been consolidated to slow wave sleep. And this is 30 seconds of sleep with 20% or greater polymorphic delta activity seen diffusely. This stage of sleep is thought to allow for memory consolidation, recovery of the brain, and probably it's due to activation of serotonin from the raphe nuclei, at least partially. And you may still see sleep spindles and other features during slow wave sleep, but it's really just defined by this polymorphic delta activity. And this is what it might look like. This is kind of a textbook example of slow wave sleep. You see all these slow polymorphic delta frequencies. Again, polymorphic means it's not like a rhythmic kind of, they all look the same in the same duration, same morphology. They all look like a different morphology. That's what polymorphic means. And you see it again here where you kind of have the slow, waveforms. And this is again stage N3 sleep or slow wave sleep. It's not as continuous, but it's greater than 20% of the record. And here's an example of slow wave sleep where you see the polymorphic delta diffusely, but you also still see some sleep spindles and whatnot in here mixed in, and that's okay. It's still graded as slow wave sleep if you see the polymorphic delta frequencies. All right, now we're reaching REM sleep or rapid eye movement sleep. This is the final stage of sleep as you progress through the stages of sleep. This is when you're dreaming. You typically get a low voltage mixed frequency EEG background that can look quite similar to the background in wakefulness. It also has distinctive sawtooth wave frequencies, which are these 2 to 6 hertz bursts. And you'll see these quite well once I point them out to you in a second here. So the most distinctive feature are just the eye movements themselves, which are rapid eye movements. So these look different than drowsiness, which were slow roving eye movements, right? You see these rapid eye movements where the patient's looking to the right here, then the left. And these are going to be kind of what you're looking for during REM sleep. This is the biggest giveaway you'll see. Here's a bit more of a subtle example of REM sleep, where you're not seeing quite as pronounced waveforms in terms of the eye movements, but they're still there. And the backgrounds you see can kind of look like wakefulness with some mix of theta and alpha frequencies and is posteriorly predominant. But you can often tell that it's not wakefulness just based on the progression of how you're getting here. You're going from sleep, they don't wake up, you start to see these eye movements, so that will help you avoid confusing this background as something that's abnormal. Here are the sawtooth waves I was mentioning to you earlier. Here's a good example how they're these kind of delta sawtooth morphology waveforms. You'll see this during during REM sleep as well. And again, here are the eye movements kind of intermixed with these sawtooth waveforms. Here's another example of the sawtooth waveforms. So hopefully that makes sense with REM sleep and the other stages of sleep. This is one of those topics you do have to invest some in just looking at enough EEGs to recognize these patterns. I think the more you kind of understand how they fit in the context of the overall EEG, the more you'll avoid being tricked by a mimicker. One of the important points to mention before we end the lecture portion here is that sleep can have transitions back to wakefulness that are really composed of some kind of rhythmic frequencies, particular delta, bursts of delta, things like that. And this is really part of a transitional state, and you don't want to confuse this as a seizure. Now, people can have seizures which wake them up too, so what you're going to look for in a seizure is different than this, but just remember this for now. We'll get to seizures when the time comes. But here's an older patient that is waking up from stage N2 sleep. You see the K complex or knock complex, maybe we called that in the past. And then all of a sudden you see a posterior dominant rhythm, and you see this kind of burst of parasagittal, frontocentral predominant, a delta, that then kind of starts to settle back down. And this is a patient that was just in a state transition and just transitioned to wakefulness, then rapidly back to drowsiness, then back asleep. This wasn't a seizure. It was something that was caused by the patient waking up very briefly out of sleep. So remember that this can occur, so you're not fooled by that. All right, this lecture wouldn't be complete without some questions. Here we go. Which type of waveform is highlighted below? In this box here, what type of waveform do you see most prominently? If you said post, you'd be correct. Posterior occipital sharp transients, again, are synchronous, posterior positive polarity waveforms seen during stage N1 of sleep. All right, is this patient here awake or asleep based on the EEG recording? If you answered awake, then clearly you didn't watch this lecture, because they are asleep with vertex waves and sleep spindles seen quite prominently here. Which stage of sleep does the EEG below indicate? I'll give you a second. Hopefully you said N2, because you see prominent K complexes and you also see sleep spindles. These are the pathognomonic findings of stage N2 non-REM sleep. Question 4. What stage of sleep is this patient in? All right, hopefully you are drawn to these characteristic eye movements, and so hopefully you picked REM sleep. This is the most kind of characteristic finding of REM sleep. We also discussed the sawtooth waves previously, so those are not present in this clip here, but that is a finding of REM sleep. Here are some references. All right, you made it. You successfully learned to read awake and asleep normal EEG in adults. That's a big milestone. That's something to stop and celebrate if you've never learned this before. If you're just reviewing, thank you for sticking with me. We're about to get to some more interesting topics if you're an EEG veteran. Up next are normal variants in adults. This is really an important topic to better understand what can be overcalled as an abnormality in adult EEG. So I'll see you next time. I'm your personal EEG tutor, Dr. Jake McKay.